Okay, welcome back from break, everybody. We're going to go on to the next for the second talk. The title of the talk is a study in real-world data races in Golang, and this will be presented by Greenberg, Vice President of Platform Engineering at Uber, and Milind, Chabbi, Staff Researcher, Programming Systems Research Team at Uber as well. Greenberg is a Vice President of Platform Engineering at Uber, leading the engineering and program management teams responsible for data center, compute, networking, storage, data, search, monitoring, developer productivity, engineering, DEI, tooling, and corporate IT infrastructure. In this role, he's the executive sponsor of the company's community of senior engineers who drive the evolution of Uber's engineering architecture, culture, and standards to be considerable more effective, reliable, and sustainable. Uber's platform engineering has offices in Bay Area, Seattle, New York, Aarhus, Denmark, Vilnius, Lithuania, Hyderabad, and Bangalore in India. In addition to sitting on the company's executive leadership team, Albert also serves as a member of Uber's Artificial Intelligence Law and Ethics Council. Prior to Uber, Albert spent 15 years at Microsoft as technical fellow and corporate vice president for Microsoft Azure Networking, leading software and hardware development and engineering across Microsoft Azure. He is the winner of the IEEE Kobayashi Award, the ACM SIGCOM Award, a winner of multiple ACM Test of Time Paper Awards, and distinguished alumni of University of Washington, CSE. He is also an ACM Fellow and a member of the National Academy of Engineering. And his partner on this talk is Milind, Chabbi. I hope I pronounced the name correctly. Forgive me if I do not. Milind is a staff researcher in the Programming Systems Research Team at Uber. He leads research initiatives across Uber in the area of compiler optimizations, high-performance parallel computing, synchronization techniques, and performance analysis tools to make large, complex computing systems reliable and efficient. I will now turn it over to our guest speakers. Over to you, Al.
Hey, it's great to hear your voice, Whale, and amazing to hear Raj's talk. Hard act to follow. So anyway, everyone, I'm here with Milind, and who's a staff programming research scientist at Uber. And Milind will do most of the talking about the work he's doing relating to programming languages, and specifically the Go programming language, which is super popular and also popular at Uber, and solving problems that arise at scale around race detection, race condition detection, and patterns, not good patterns, but patterns that come up in large code corpuses. Before I dive in, I just wanted to give you a little bit of context. Uber is a verb, it's a noun, and so we do a ton of AI, referencing Raj's talk, and we don't just do this AI, global match in the cloud, but we fulfill. So it's an application across the entire planet that does if you will, a global match in the cloud using AI and other computational techniques, data techniques, and then things and people move and try to move efficiently and with a reliable ETA. So there's lots of interesting systems problems, and those systems problems lead to, we write a lot of software, which leads to the talk that we'll talk about here. So here's just a bit of numbers, give you the lay of the land of the scale at Uber. It's really massive scale, and I don't want to go through and drain all the numbers, but I'll give you a couple of highlights. So Uber runs a little over 4,000 microservices. That cloud of dots on the left-hand side with links between them is a depiction of the 4,000 microservices and their communication patterns. Now, much of this is written in today in Go. you know, Go is very pleasant to use programming language. To me, it's familiar. If you've written in C, then it's C or C++ or even Java. It's got many of the things that you're familiar with, but it's quite easy to use, and that's what attracts programmers to it. And we'll get to the problems that come with that as well in a minute. It's a great opportunity for me and an honor to be part of developing the code that, you know, reaches billions of people every month, helping them to go to where they need to go and get what they need to get through Uber. And, you know, the business is doing great. And you know, just last week we had a nice earnings report. I'll throw that in there, even though it's an academic audience, that indicates that we're growing fast, and we're super excited about the prospects for this business. Now, this brings me to the point where I want to, you know, get to, you know, the community here. It's a you know, given this vertical that we're working on, the transport vertical, it really cuts through everything in computing. And my not so hidden agenda, besides just, you know, talking and sharing knowledge, is, you know, we do have a ton of open positions for engineering here at Uber. And if you like the AI stuff that Raj talked about, or you like distributed systems, or you like programming languages, the kind of thing that Milind is talking about, we'd love to hear from you. So please keep that in mind. The one thing that I want to say is that, you know, when you're working on problems at the scale, at, you know, really high scale, then you do hit many of the problems that Raj talked about, where you know, the what's out there in the public domain, it doesn't work. It's or the data's missing, or the algorithms are missing, and yet you need to make progress and get, you know, iterate and get better. And this leads us to put a huge focus on developer productivity, which is the area that Milind works in. And we picked the Go programming language because it helps to make developers productive. In particular, you can express concurrency very simply in Go. On the other hand, simple expression doesn't hide deep and hard problems, and therefore, you know, there will be tough problems that you know, if we don't fix them early, the system will fall into and have bugs or outages. So the kind of research and the kind of output that Milind is going to talk about is how we add value to the ecosystem that develops these programming languages and distributed systems, to make sure that we catch these problems by code analysis and don't get them out, don't let them out into the wild where they might impact customers. And with that, I'm going to turn it over to Milind.
Thank you. As Albert mentioned, Go is a very popular language inside Uber for developing microservices and even tools. So this talk is focused on Go and the kinds of concurrency issues that we face and what we have done to address them. For those who may not be exposed to Go, Go is a compiled, statically typed, type-safe, memory-safe, garbage-collected language. It is like C, it's a touch of Python to it because of the kind of minimalism it has adopted. It's really embraced in microservice development environments, and there is a huge list of industries in various domains that have adopted Go for writing microservices. One very special thing of Go is that the concurrency is a first-class citizen. You can prefix any function invocation like this one with the keyword Go, and that function runs asynchronously with rest of the other entities in Go. And those entities are called as goroutines. Goroutines are lightweight user space threads. They actually context switch over underlying OS threads. And Go runtime provides a lot of facilities so that it automatically context switches whenever one goroutine is about to block. So in this concurrent programming language world, multiple goroutines can communicate either using shared memory, which happens to be the most common way of communicating and sharing data between goroutines, and also using message passing using what are known as channels, even though those channels are in the same address space. At Uber, Go is our primary programming language of choice for developing microservices. We have over 50 million lines of Go code, and there are more than 3,000 services that are written in Go, and they run on millions of CPU cores. We also have other languages in which we write microservices, the primary ones being Java and Node.js. Go programs exhibit significantly more use of concurrency and synchronization constructs compared to microservices written in other languages such as Java. And we did a comparison of microservices in these two languages, and we found out that the points where concurrency is created is about 1.5 times more in Go code compared to Java code. So concurrency creation could be like Go in Go language, or it could be thread create, something like that in Java. There is about 5.5 times more point-to-point synchronization constructs per line of code in Go compared to Java. What are point-to-point synchronization constructs? Things like locks and condition variables, right? And there is about 18.5 times more use of group synchronization constructs per line of code in Go compared to Java. But group synchronization constructs are things like barriers, which are also called as group weights in Go. Clearly, people are using a lot many more synchronization creation and concurrency constructs in Go compared to, say, Java, just when you look at code statically. Even when we dynamically profile programs running on these millions of CPU cores and inspect them, Java versus Go, what we noticed is that on average, there are about 2,000 goroutines in a running production microservice, whereas there are about 256 threads in Java. That's about 8 times more in Go compared to Java. So more concurrency can lead to more concurrency bugs. And of particular interest to us was data races. In Go, data races happen when 2 or more goroutines concurrently access same shared variable, and at least one of them is performing a write operation. And it is well defined in other languages too. In Go, it happens whenever 2 goroutines are involved. In other languages such as Java, it is when 2 threads are involved. So in the rest of this talk, I would like to cover 2 pieces. One, deployment of a dynamic data race detector at Uber scale. And 2, what we learned by finding those data races and what are the patterns of data races special to Go. Go actually ships with a dynamic data race detector. To run that, one has to compile code, recompile code with instrumentation, which instruments all memory accesses. And at runtime, it performs a dynamic analysis that is built on top of the time-tested thread sanitizer, and it uses what is known as a happens before analysis. It basically tries to prove whether 2 accesses by 2 goroutines are ordered or unordered, and unordered access is considered as a data race. The race detector is aware of goroutines, just not threads, and it's also aware of Go's synchronization constructs, which helps it build these happen before relationships. Now, a thing to note is that the dynamic race detector does not explore all schedules. By that, I mean a race that is exhibited in one run may not be exhibited in another run, even for the same input. So it's fundamentally non-deterministic in nature. And the race detection will introduce about 2 times more compilation overhead, 2 to 20 times more runtime overhead, about 5 to 10 times more memory overhead. Go has very rich testing facility, and testing is a built-in feature. So running data race detection, dynamic data race detection on unit tests across the repository is a good starting point. And at Uber, our Go monorepo, where most of our services lie, has over 100,000 unit tests. So when should we run a dynamic data race detector? There are 2 choices. One is during build time, prior to when a developer is about to merge a code patch. And we have a very high throughput of code patches coming into our system, which runs into thousands to tens of thousands per day. So what can we do? If we run the race detector at build time, and if we find a race, we can block such patches. The good thing about that is it helps in an early detection. However, patches can easily slip through data race detection because of the non-determinism in schedule that I just mentioned, that existing race may not be exhibited. Consequence of this is that a later patch developed by some other developer may be incorrectly blocked because that may exercise the schedule where data race exists, but it was introduced by a previous patch. So it can look very noisy and hurt developer experience. Instead of blocking a patch, one can say we can only warn that there exists a data race. Good thing is that, again, it is an early detection strategy. However, it can be very noisy due to pre-existing data races in the system. And if it is just a warning, developers easily become immune to them and ignore data race reports. In either of these approaches, which are compile time or a patch delivery time, we have high build time because the dynamic data race detector has overheads, and it can easily violate SLAs needed for a continuous integration system. An alternative approach is to run the race detector post facto after the patch is already accepted. So we can take a daily snapshot of the code and run the race detection on the entire repo. So in one shot, we will be getting a huge list of data races. So we benefit by batch processing. There is no exposed build time overhead that slows down our development. We will never incorrectly block a patch due to an irrelevant report because it's never blocking any developer submitted patch. An advantage is also that over time, we will explore more and more schedules and detect more and more data races. The flip side of this is that the bug detection is a little late. And once it is detected, we need to find an assignee for such a defect. And also we have to make sure that bugs that are repeatedly found are not duplicated. So these last 2 problems we can quite easily solve by the assignee problem we can solve by piggybacking on the code history and the changes, and also large industrial settings have a pretty decent bug triaging system. So they eventually find their ways to the right person who is supposed to fix it. And for bug duplication, we use the call stacks where the data race is found, and we compute heuristically, we compute a bug hash that helps us identify whether two bugs are same. That eliminates us from filing repeated bugs. And this post-facto approach is the one that we adopted. That's our choice. So the way it looks is like this. We have a large repository, and on a regular basis, we run all unit tests with dynamic data race detector. Among all the detected races, we perform a deduplication. And if we identify that we have found a new data race, we generate tasks and assign them to appropriate teams, who then later fix them locally and deliver patches. This system has been functional for last about 1.5 years. And in this 1.5 year period, we originally imagined, well, Go has data races, maybe we will find some. We found not 1, not 10, not 100, not 1,000, about 3,500 data races in Go code. With the help of our developers, we also fixed about 2,000 data races. And there were more than 600 unique engineers involved in this effort. And they delivered together about 1,200 patches. Also, this system finds 10 to 20 new data races every day in newly written code. So what you are seeing here on the graph is on the x-axis, the passage of time, and on the y-axis, the cumulative number of bugs found and fixed. We started somewhere around April of 2021. We were initially tinkering with our system and filing only a few number of bugs. That went on for some time, and eventually we opened our floodgates. That was around July of 2021. We kind of filed all the bugs, and that also coincided with about the time when a lot of bugs got fixed. We were hoping that that may be the end of it, but the system kept on finding new races, and we were finding at a rate more than the rate at which one could fix it. Around this time, March of 2021, we further improved our tooling, where initially we were intentionally not filing certain types of bugs because it was harder to find an assignee. We improved that system, and we ended up we started filing at a much larger rate. Around April of 2022, we have started a strong initiative within the company to improve code quality, and you can notice that there is a significant improvement in the rate at which our developers have been fixing data races. So we also looked at almost every fixed bug and classified them based on different root causes and found very interesting patterns. That leads me into the second portion of this talk, which is about Go data race patterns. And I will give a few examples where I will tell you the data race, some basics about Go syntax along the way. The first observation we made is that in Go, transparent capture by reference of free variables in goroutines is a recipe for data races. What do I mean by that? So here is an example where somebody has written a piece of code where there is a loop. It is iterating over items, and for each item, the developer writes a anonymous function. It's also called as a lambda or a transparent goroutine. And presumably processing that item is expensive, takes time, and they are making use of concurrency so that while the processing of one item is happening, it can create another goroutine and it may concurrently process the next item, right? That's what they are doing here. And there exists a data race here where the item here is a free variable, meaning it's not defined within the scope of this nested function. Whenever there is a free variable in a anonymous function like this, the Go language's semantics is that it captures it from the surrounding scope, and the capture is by reference, which is different from other languages. For example, in Java, capture by reference inside a lambda is never allowed. In C++, the developer has to explicitly state whether a free variable is to be captured by value or by reference. Whereas in Go, it is always default capture by reference. So now what's happening is a bunch of Go routines are running here, and the outer loop is a Go routine in itself, which is creating these concurrent Go routines. And as one Go routine is trying to access this item, the outer Go routine is changing that reference to point to the next item, causing a data race. This is a read, that's a write, and there is no ordering, that's a data race. This happens whether we are ranging over maps, slices, arrays, whether there is a read or a write, whether item is a value type or a pointer type. And this is a very common data race that happens in Go. The second pattern we noticed is concurrent accesses to Go's built-in thread-unsafe maps. Go has a built-in map construct. Map is a hash map, like a hash table. It is built in, any key and value type can be put into a map, but it is not thread safe. So here, the developer creates a result map of key type, user ID, and value type of string. And then for a range of UUIDs, it creates one Go routine per user ID to process each item. Presumably, each processing is somewhat expensive. That's why they are making use of concurrency. And each processed item is inserted into this result map with a key and the processed result. Here, the developer is under the assumption that each key is unique. So inserting different keys into this data structure is presumably safe because they must be indexing into different locations. But a map is a sparse data structure, unlike an array, which is a dense data structure. So concurrently reading while writing or concurrently writing into a map, even though it may be on two different keys, is a racy situation. And this leads to a data race on maps. Now, data races due to thread unsafe maps is nothing new and is not to Go as a language. It happens in any language, say Java or C++. But the fact that map is a built-in data structure, built in a language construct, plus its syntax is like array accesses, makes developer easily make this mistake, especially in the context of creating Go routines. And when we profile our code and assess the use of maps, we notice that people developing Go code happen to use 1.35 times more per line of code use of maps compared to other languages such as Java. So more extensive use of maps and easy to create concurrency together make it problematic and create data races. The next observation is mixing message passing with shared memory can cause subtle data races. So I mentioned that in Go, two Go routines can communicate with one another, either using shared memory or using message passing. And when one mixes both of them, it starts to cause trouble if it is not done correctly. So here is an example where the developer has written what is known as a future. A future is a construct where you create an asynchronous function, and at later point, you want to wait for its completion. So a future here has a start operation on it and a wait operation on it. So the way future start is implemented is some function pointer is registered with the future, and whenever start is invoked, it creates a goroutine and invokes that goroutine invokes the function pointer. But the start itself returns immediately after creating such goroutine. It is non-blocking. This goroutine itself, after finishing execution of that function pointer, sends a message on a channel. CH is a channel here, where the left arrow is sending a message on a channel, and these channels are blocking. And whenever whoever invoked the start wants to get the results from wait, fetches the message from the channel, which is again a blocking operation. If wait is performed prior to completion of this goroutine, this blocks, and it unblocks only when the function completes. So far, so good. There is no problem here. But the developer makes a little bit more changes around it, where they say that either when there is completion of the async function or when a timeout happens, I want to end my wait. And this is very common in transaction processing systems with deadlines, because you may not want to wait forever for something to finish. So if a timeout happens, we want to return. And the select statement in Go is used to wait on multiple things, and whichever arm is ready is the one that executes. And if both are ready, one of them is chosen arbitrarily. So here, assume that the wait is called and the timeout happens. In that case, this code sets the result as a timeout error. At the same time, this asynchronous function could be finishing and writing to the same result variable, leading to a data race on the access to result variable. So what we noticed here is this write is a shared variable write in the presence of goroutines channel. Mixing them causes a subtle data race. The last point I want to discuss is related to Go's transparent conversion between value types and pointer types, and Go's use of same syntax for both value and pointer types. Here is a struct in Go. It's a type, and the structure's name is mystruct. It has got, let's say, two fields, A and B, both are integers. In Go, instead of saying int A, we say A int. And one can write operations on these structures, similar to methods on objects, right? Where on mystruct O object, we can have a method called read A. Let's say it returns an integer, which simply returns the value of A field of this object. And one can write, say, write B, which takes a value that sets the value B to V. Here, this is a syntax error. This should be O. Here, notice a subtle difference that read is performed on O, whereas write is performed on the pointer to mystruct instead of just struct. That's the difference. Whenever something is invoked on the value type, the whole object is copied. Whereas whenever something is invoked on a pointer type, the operation is on the same object. This is allowed in Go. In other languages such as C++ or Java, O here is like this pointer, and which is always a pointer. You always operate on the pointer type, not on the value type. So let's see what kind of a trouble it can create in a code like this. So here we have an object which is mystruct, and it has A equals 42, B equals 24. And the developer says, let's concurrently do operations, one that writes to B and one that reads from A. Now they are two different fields of an object, and there should be no race because they are two different things, two different memory locations. So then we have these two things happening. This right of B is invoked on the object pointer. So the object that is created here is the one that gets modified with value. However, the read of A, because it is performed on the value type, first it makes a copy of this object and then reads the value at A. So while this copy is being made, it is copying not only A, but B also. And while this B is being copied, the same B is being overwritten in the write operation, leading to a very, very subtle data race that's not at all obvious for a common developer. This is something that happens under the hood in the compiler code generation. There are other observations we made. I'll not go into the details of that. Go offers more leeway in its group synchronization construct that leads to a lot of data races. Go has dynamic arrays. They are called as slices, and they are very confusing types. They lead to hard to diagnose data races. And a vast category of data races also happen because we write a lot of tests, exercise APIs in parallel, and those APIs may not be fundamentally written to be thread safe. That's another cause of data races. Okay, so sifting through a lot of these data races, we categorize them into these two broad categories. One is Go specific data races, and the other one is not Go specific races. On the left side, among the Go specific data races, the the dynamic array, which is called a slice, is the most common one involved in data races. I didn't go into an example of this. And then the second one is concurrent tests exercising thread-unsafe APIs. The capture by reference example, which was the first one I showed, is one of the top ones, followed by concurrent maps. Go does not have volatile types. That leads to certain kind of data races, which is common in Go. The data races related to confusion between value and a pointer and message passing and shared memory are less common, but whenever they happen, they are very hard to diagnose and debug. In the category of not Go specific data races, forgetting to protect a critical section with lock or partially protecting it, which is nothing language specific, is the most common one. In fact, it is more prevalent than language specific ones. And then there are other set of classes in which data races happen. Something we noticed was user written synchronization, meaning user code writes some kind of handwritten synchronization, is very uncommon. In fact, it was zero for a long time. Eventually we found one, which is different from some of the findings that other researchers did almost 2 decades ago in their study of data races or other concurrency bugs in C and C++, where one of the most common causes of concurrency bugs was user-written synchronization. In Go, developers usually don't write their own handwritten synchronization. They rely on the library provided synchronizations. Okay, so to conclude, it's very easy to write concurrent code in Go. There is complex interplay between Go language features and concurrency, which makes it very easy to introduce data races in Go. There are interesting trade-offs on where to deploy dynamic data race detection in a continuous integration system. Dynamic data race detection in Go at Uber helped us find 3,500 data races in our 57 million lines of Go code. It helps us fix more than 2,000 data races, and the remaining ones, we are working actively to fix them. It's helping us detect data races on daily basis. There are a lot of things to do this. We have barely scratched the surface of concurrency bugs in Go. while we used only on unit tests, our future direction is to do this in production using some lightweight race detection techniques that might use certain hardware facilities. We are also very interested in automatically root causing data races and fixing them automatically so that we can reduce burden on developers. So these are some of the active topics we are working on. Here is my contact information. Feel free to contact me, either if you want to understand more about this or if you're interested to work on these kinds of topics or interested in Uber in general. So with that, I would like to hand it over back to Albert, and also that later we'll open up for questions.
Hey, thanks a lot. Yeah, we'd love to get feedback, love to get questions. These are hard problems, and you know, this team that Milind is on goes across all the programming languages that he mentioned, Java and Go, and we're also in the machine learning area big users of the Python language. So anything around this talk in particular, you know, the hard problems of managing large code bases, making lots of developers happy, and making the code correct by finding these kind of race conditions. We'd love to hear more. I'd love to hear your thoughts and your questions.
A question here. This is really very interesting. You compare Go with Java in your presentation. I was wondering whether you consider other programming languages like Pascal or Argo 68 as well in your analysis.
That's a great question. I think a broader comparison should have involved many more languages. Internally, most of our services are either in Java or Go, and a kind of an apples to apples comparison to make between two codes trying to accomplish somewhat similar things was comparing Java versus Go within our own code base. So short answer, we did not compare with Algol or Pascal, or even C++ for that matter.
Thank you for a very, very informative talk. It's a very challenging issue. And the size of code and the complexity of code that you do at Uber obviously require you to do some difficult analysis. One question I have, is there anybody, or maybe at Uber, are you trying to also try to help the developers by doing some static analysis tool that can catch those patterns that lead to these type of race conditions?
Yeah, that's a great question. Yes, we originally began this by exploring all possibilities. Static analysis tool, dynamic analysis tools. We tried some static analysis tool originally for our Java code base. In Go, we did not have access to any of them. One of the difficulties we had with the static analysis tools was the false positive rate. Static analysis tools, you can use them at compile time, or at patch merge time. And they had a lot of false positives, and if we had to bring them on board, we really had to drive down the false positive rate. Otherwise, they were creating a bad developer experience. And at the rate at which our developers create code, it was not sustainable. Hence, dynamic analysis was a better choice here, because every detected race in a dynamic analysis is a true positive. It may have false negatives, meaning there may exist a data race that we may not detect, but it was really important for us to not block developers due to false data races. So with that in mind, this was our choice. Now, circling back, having learned what are the patterns of data races commonly found in our code base, now we have better ideas on what simple, easier linters that we can write and use them as static analysis tools during code compilation time.
Hi, Milind. I had a question. I was just curious on what these data races, like what the impact is on Uber users, and why is it so important to detect and fix these bugs?
Yeah. So two answers to that. One is I would like to take the approach of Hans Boehm, where if you have read that data race paper from Hans Boehm, that there is no such thing called as a benign data race, meaning every data race, you can assume that you have no idea what may happen. It can crash and burn the system, even though it may not be doing so right now, or it may not be exercised right now. But among the category of races we have seen things that would lead to producing incorrect metrics, things that would crash the system, things that would compute credit card balance incorrectly, those types of things. So the consequences can be bad user experience. In the worst case, bringing down an entire service, which means lack of loss of service for our developers. So there is a broad category. I won't say that all the 3,500 data races we have found would fall in that category, but even if we have prevented only a handful of them, it's a win for us, because the loss is substantial when they happen in production.